In this video, we'll look at an application of the probabilistic method to extremal set theory. Extremal set theory is an area of combinatorics concerned with questions such as, what is the largest collection of sets that satisfy certain desired properties? And the question that we'll look at in this video is the following. What is the largest antichain? And more precisely, what is the largest collection of subsets of some ground set, numbers 1 through n, so this is an n-element set. So I want as many sets as we can such that none of these sets is a subset of another set. Okay? So this is what we mean by an antichain. And for a given value of n, what is the largest number of sets you can have? What is the largest L that we can have as a function of n? To give an example, when n equals to 3, you can have the sets 1, 2, 1, 3, and 2, 3. And you see that none of these sets is a superset of another. More generally, when you take all k-element subsets of 1 through n, this collection also has the property that no set is a subset of another set, because all these k-element subsets have the same size, so none of them can contain another. Now, this collection of sets have n choose k sets. And which value of k maximizes this quantity n choose k? Well, it is maximized at k being n over 2, or when n is odd, I can either round down or round up, leading to n choose k over 2, or the floor of k over 2. So this is so n choose n over 2. So n over 2 floor, meaning that's rounded down, or equivalently rounded up, will produce the same answer. So this many sets we can get forming an antichain. Now, this is just one example. And the question is this the best example? Can we do better? Can we get an even larger collection of sets that form an antichain? And the classic result of Sperner, so Sperner's theorem, says that actually, no, this is the best that we can do. And what the theorem says is that if you have L subsets of 1 through n, such that none of the sets is a subset of another, then in fact L is at most n choose the floor of n over 2. Okay? So this answers the question that we were asking. And in this video, we'll use the probabilistic method to prove Sperner's theorem. And it's quite a beautiful proof. And the introduction of randomness into the proof is quite remarkable for a theorem that really doesn't involve any randomness at all. What we will prove is actually the following theorem, which is slightly stronger than Sperner's theorem. And we'll prove the following, also known as the LIM inequality, named after 3 people who discovered the theorem. And it says that in the hypothesis that we just set up, we furthermore have the following consequence. If you take the sum over I from I being 1 to L of the quantity 1 over n choose the size of AI, then this sum is at most 1. Okay. So let us first prove this LYM inequality. And then afterwards, we'll deduce Sperner's theorem from this LYM inequality. Let's now introduce randomness into the problem. So let sigma 1 through sigma n be a randomly chosen permutation of numbers 1 through n. And here, we'll choose this permutation uniformly at random, meaning that of all the n factorial different permutations, we'll select one with equal probability of being any one of those n factorial permutations. And now let's consider the following chain of sets. Starting with the empty set, and then the set containing just the first element of this permutation, sigma 1, and then the set containing the first two elements of this permutation, sigma 1, sigma 2, and so on, until we add all the elements into the set. Okay? So these are the set of prefixes of this permutation, where we add one element at a time. So this is a chain of subsets of 1 through n. And let's consider the event for which we'll evaluate its probability. So the event that AI, so AI is one of the sets that was originally given in the theorem statement. So what's the event? So the event that we'll consider is the event that AI appears in this chain. Okay, so this chain means this chain over here. Now, this chain is random because the sigmas are a random permutation. Now, even though the AIs are deterministic, the AIs are given, this permutation is random. So this is some event for which has a probability. Now, when do we have AI appearing in this chain? Well, if all the elements of AI appear in this permutation before all the non-elements of AI. So we can count how many different ways this can happen. So of all the n factorial different permutations, the number of permutations where the elements of AI appear first is AI size factorial, and then all the non-elements of AI appear afterwards. It's n minus the size of AI factorial. And this quantity here is equal to 1 over the binomial coefficient and choose the size of AI. OK. Next, let us note the following, that no two different AIs, AJs, can simultaneously appear in the chain. Why is that? Well, we assumed that no AI is a subset of another AJ. And if indeed you had AI and AJ both appearing in the chain, then one of them would contain another. So this chain cannot contain two different AIs at the same time. And therefore, these events meaning these events over here are disjoint as we run I from 1 through L. If these events are disjoint, and each of them have this probability, well, the sum of these probabilities then must add up to at most 1. And that's indeed the conclusion that we're looking for. So the sum of these probabilities probability that AI appears in the chain, in this random chain. The sum of these probabilities add up to at most 1 because these events are disjoint from each other. And we had calculated earlier that the event probabilities are given as 1 over n choose the size of AI. Okay. So this concludes the proof of the LYM inequality. You see the final line, the final inequality is precisely what we were trying to establish. And finally, let us prove Sperner's theorem by deducing this theorem from the LYM inequality. So this is a quick deduction because n choose the size of AI is at most n choose the floor of n over 2 for all I. Right? So the binomial coefficients for a given n maxes out in the middle. We have this inequality. And thus, here I'm just rewriting the LYM inequality. The sum from so I from 1 to L of 1 over n choose size of AI. This is at most 1, so that's what we just proved. And then applying this individual bound to each term, we get L different terms, and each one of them in the denominator, we have n choose the floor of n over 2. And rearranging this inequality, we get the desired upper bound on L. So this concludes the proof of Sperner's theorem. And it's a beautiful result with a beautiful proof that is a wonderful illustration of the probabilistic method in combinatorics, where although the theorem statement itself is deterministic, doesn't involve any randomness, the proof works by introducing randomness into the problem. So this is an application of the probabilistic method in combinatorics, and I think is one of the most beautiful applications.